we're going to cover the fundamental theorem of calculus, or FTC for short, and then the indefinite integral. So let's get started with FTC. Thus far, you've learned about two branches of calculus. So it's differential calculus, and you would have touched on integral calculus. Now, the fundamental theorem of calculus is a theorem that relates the two branches of calculus as inverse processes of each other. What does that mean? For example, consider subtraction, which is the inverse of addition, right? You add two numbers, the opposite of adding two numbers is subtracting two numbers, okay? Division is the inverse of multiplication, okay? That means to undo multiplication, you perform division, or to undo division, you perform multiplication. And you will now learn that differentiation is the inverse of integration and vice versa. So to undo differentiation, in a sense, you can think about integrating. And then to undo integrating, you can do differentiation. So that's what we have. Differential and integral, or differentiation and integration, are inverse processes, just like we have subtraction and addition being inverse, and division and multiplication being inverse processes. So, the fundamental theorem of calculus, FTC, it has two parts. There's part one and there's part two. Let's cover part one. If f is a continuous function on the closed interval a to b, and these are just basically input values, okay, so from 1 to 7 or -2 to 100, right? Then the function g defined by, so we have this function g of x is equal to the integral from a, okay, there's that a, that's the starting point of your closed interval that you're considering. It's taking the integral to x, so there's that variable x. You have the variable x being the input into the g function, and here it is in the upper limit of this integral. So g of x is the integral from a to x of the f function, so f of t integrated with respect to t. And obviously, x must be between a and b, and it can be inclusive because we are looking at it over this interval. So if this is the case, if g of x is defined like this, basically g of x is the integration of the f function, then okay, g of x is continuous on the closed interval a to b, and it's differentiable, okay, on the open interval a to b. And the most important thing, or the key takeaway here, is that the derivative g prime of x of this function is simply equal to f of x. So we take that function there that's being integrated, and we just substitute in that upper variable, that x variable that's in the upper limit, to get the derivative of g of x. Now I know it sounds tricky at first, but I'm going to show you an easier way of representing FTC part 1. So let's just go through what the notes indicate. So what does this theorem actually mean? The theorem states that if you integrate a function, so the function that we are integrating, take a moment to see if you can identify it. The function that we are integrating is the f function. Okay, that's the function we've been given. So we are integrating a function, in this case, the f function, and we're integrating it from a to x. And then we get that integral, and then we differentiate the integral, right? You will obtain the original function evaluated at the upper limit. So what I'm doing is I'm integrating it, and that's going to give me g of x. And to get g prime of x, I obviously have to differentiate what I've circled in blue. Once I differentiate what I've circled in blue, I'm just going to get that f of x function, and I say it's evaluated at the upper limit because we're just substituting x in place of t. Okay, the dummy, you can think of t as a dummy variable, right? In this case, the upper limit of the integral is x. Okay, so that's one way of seeing FTC part 1. An easier way that I like to remember it is as follows. So, an easier way to understand part 1 of the FTC is this. So instead of introducing that whole g of x and g prime of x, I like to think about it like this. So I'm going to give you the f function. There we go. And it's dealing with, I like to call it a dummy variable t. So we are going to integrate that function, and it's from a to x. And then we're going to get that integral. But then what I'm going to do is I'm going to differentiate it. So I'm integrating the f function from a to x, and then I'm differentiating it with respect, okay, to the upper limit, which is the variable x. So I'm integrating and then I'm differentiating, and if I do that, I'm going to get that exact same function f back. Only this time I'm not using the dummy variable anymore. It's going to be evaluated at it's going to be using the upper limit, which in this case is a variable, okay, which is x. So all you're doing is when you integrate and then differentiate, all you have to do is take that x and substitute it wherever you see t in that f function, right? Another thing to note that the value of the lower limit, and in this case it's a, it does not affect the final function that we obtain, okay? So that's an easy way to remember FTC part 1. I have a function f, okay, and then I'm going to integrate the function f with respect to t, and I'm going from a to x. So I've just got my integral, and then what I'm going to do is I take my integral and I differentiate it. And this is going to give me the exact same function f that I had, just evaluated at that upper limit, which is the variable x. So wherever I see t in their function, I'm going to replace it with x. That's basically an easier way to understand FTC part 1 instead of introducing that whole g of x. If you understand it like that, it's fine. I like this way of understanding it. Let's do an example and see how this works. Exercise 1. I want you to find the derivative of the function p of x given, and I've given you the function p of x. So take a minute and try it. It's super easy. All right, let's go for this example. So we need to get the derivative of the function p of x. So basically I need to get p prime of x. Now here's p of x. So what do I need to do to get p prime of x? I need to take this function here and differentiate it with respect to x because p is in terms of x. So I need to take the derivative of the p of x function. Okay, so this is equal to the derivative of the p of x function. And what's the p of x function? It's this integral right here. So it's the integral from minus 7 to x of 1 over the cube root of m minus 5m squared integrated with respect to m, so dm. And then how do we, so let's just take this out for a minute so you can see. How do we solve this? This is just FTC part 1. It states that when you're doing this derivative, just take the variable in the upper limit and substitute it wherever you see the dummy variable. So it's going to become 1 over the cube root of, I see an m here, I'm going to replace it with x. I see an m there, I'm going to replace it with x. There we go. That's your answer. That's how simple this example is. Okay, let's move on. Exercise 2, again, differentiate the following with respect to v. Okay, let's do this. So this is super easy. We just need to differentiate that integral with respect to v, which is the variable in the upper limit. My dummy variable in this case is t. Super easy, apply FTC part 1. So I'm just going to take v and replace t wherever I see it. This is going to be equal to 1 over e to the power v. So that is the derivative of this function here, or that integral. Right. Let's move on. Exercise 3. Now, in this example, again, I want you to solve this, basically get the derivative. However, in this example, I want you to note the upper limit, right? You have 2x cubed as the upper limit, whereas in the actual representation of FTC part 1, when I introduced it to you, and in the previous 2 examples that we did, we always had x, or in the previous example, we had v in the upper limit. We just had the variable on its own. In this example now, we have a function of that variable we are differentiating with respect to. So, since we have a function of that variable, I've given you a hint, you need to use the chain rule in conjunction with FTC1. So take a minute, try it, and then I'll go through it. All right, let's go for it. So before I actually find the derivative, let's just work with some notation. What I'm going to do is I'm going to say let y equal to the integral 0 to x cubed t squared dt. And if you don't want to do this, it's perfectly fine. You can go straight into the answer. I just like to have my workout neat. So we have y is equal to the integral, and we need to find the derivative with respect to x of y. In other words, we need to find dy dx. Okay, dy dx. That's what we need to have. Okay, now because we don't just have x in the upper limit, okay, but we have a function of x, you must use the chain rule. So you have to use the chain rule. Therefore, what I'm going to do is I'm going to say let u equal to 2x cubed. Okay, we need to have u equals to 2x cubed. Then our goal is to find dy dx. I can find dy dx by calculating dy over du, or dy du, and multiplying it by du dx. That's the chain rule. And I like to think about these in terms of fractions. So this one cancels out that one, and I'll get left with dy over dx, which is what I want. But important to note, they aren't fractions. But again, it's helpful to think of them as if they are fractions. Okay, they're derivatives. So we need to find dy du. Okay, so this is equal to. Now, dy du, let's rewrite this out in terms of u. Okay, so it will be equal to 0 u t squared dt, and we are now differentiating that with respect to u. So all you need to do now, since we have a single variable in the upper limit, is wherever you see the dummy variable in that function, replace the t in this case, which is the dummy variable, with u. So we will have u squared. Okay, there we go. And then what we are going to do is we need to multiply dy du, in this case it's u squared, by du dx. So I'm going to differentiate this with respect to x. So differentiate this with respect to x, it's going to become multiplied by 6x squared. Okay, and then we need to have everything in terms of x again because u is a variable that we introduced. So u is equal to 2x cubed. So it's 2x cubed all squared multiplied by 6x squared. Okay, so that is going to become 4x to the power 6 multiplied by 6x squared, and that will give us 24x to the power 8. There's your derivative. Okay, so this right here, that's the derivative of that. Okay, it's the derivative of this function here, that integral. All right, that's exercise 3.